Okay, we are going to be solving question 3.90 from the Heat Match Transfer 8th edition textbook. Here we will be checking out extended surfaces, the real important task used for a lot of diffusion of heat. A lot of heat exchangers and things like that are used, or use this technique to dissolve some of the heat from the base. So, reading from this question, it says, one method that is used to grow nanowires or nanotubes with solid cores is to initially deposit a small droplet of liquid catalyst onto a flat surface. The surface and catalyst are heated and simultaneously exposed to a higher temperature, low pressure gas that contains a mixture of chemical species from which the nanowire is to be formed. The catalytic liquid slowly absorbs the species from the gas through its top surface and converts that into a solid material, is deposited onto the underlying liquid-solid interface, resulting in construction of that nanowire. The liquid catalyst remains suspended at the tip of the nanowire. So jumping into our variables and and values, properties, and the questions, it says, consider growth of a 15 nanometer diameter silicon carbide nanowire onto a silicon carbide surface. The surface is maintained at a temperature of Ts equals 2400 Kelvin, and the particular liquid catalyst that is used must be maintained in the range of 2400 K to 300 K, or 3000 K, sorry, to perform its function. And we have to determine the maximum length of the nanowire that may be grown from the conditions characterized by H equals 10 to the 5th watts per meter squared Kelvin and T infinity of 8000 Kelvin. We are assuming properties of the nanowires are the same for the bulk silicon carbide. So it follows up with a quick little schematic here. So this is the start, the initial time, and then as time continues on and the heat is exposed to the catalyst, we then develop the growth. So starting off, I just wrote my given statement, which is just a summary of the stuff that they gave us in the question. And then our find is the maximum length of the nanowire. Here's my schematic. Pretty good, I would say, compared to the given one. That's why I have the textbook open, so you can actually see a good schematic rather than mine. And then our assumptions, we know that it's going to be a steady state question for where we're at right now. And then it's also an extended surface solution. So, heavy reliance on the textbook here. We were looking at fins of uniform cross-sectional area. So here we have the exact same problem here, or sorry, it's kind of geometry here. So we're going to follow most of these equations. So here we would need to find a m value. This m value is going to be fitted into this function right here. As you can see, m is shown quite a bit of times. And this will be used to solve for the length. We can see that there are L terms in here, but that's getting ahead of ourselves. So first we must solve the m squared problem. So I just moved the squared term over, so we know that it's going to be m is equal to the square root of hp over kac. So up here it says that p is equal to pi times d, and then our ac is pi d squared over 4. So breaking down these two components, we can then solve this equation using these terms. So it's 4 times h over k times d. For the material, I found that the k value is 30 watts per meter squared, or watts per meter Kelvin. Our d is 15 times 10 to the negative 9th meters. And our h value is 10 to the 5th watts per meter squared Kelvin. So we get an M value of 942,809.04. So we know that our temperature ratio is equivalent to that function I showed before down here. But that is also equal to the temperature minus, or the range that we were given here. So it's T minus T infinity over T of the base minus T infinity. So actually, I don't believe this is a steady state problem. So I'm sorry, I'm not sure if we should write that down. There's no mention of real, or there is a mention of time. So I guess it's not really a steady state problem. But another assumption that you could say is constant properties throughout, and it's constant properties from the extended surface and the base as well. So sorry, back to that. So we know that our range of temperatures, we got to stay within the 3,000 and then also the 2400, subtracting by the ambient temperatures is equal to 0.893. So that will be equal to all of this over on the left side over here where my cursor is. So just to solve in steps, I solve for H over MK, which I got a value of 0.035. We know that we are trying to solve for the length, so we're going to plug in x equals L. So here, L minus L, cosh of M is going to be equal to, or cosh of 1 is going to be equal to 1. Or sorry, cosh of 0 is going to be equal to 1. And then sine of 0, or sine hyperbolic is going to be equal to 0. So 1 plus 0 on the numerator, and then below us on the denominator, it's hyperbolic cosine of ml plus that term that we solved for before, multiplied by hyperbolic sine of ml. So I wrote that down here. Sorry, these numbers are kind of jumbled, but it's just our m value here multiplied by L. We do not know L. So from here, we have everything filled out except for L. And the best way that I would say to solve this is to just plug and chug kind of different L values to see if we get equivalent values on the left side to the right side. So since we know that the diameter is going to be substantially smaller than the extended length of the surface or of the fin, we could start with a significantly larger number than the diameter. So I chose 250 nanometers to start. So plugging that value in, and then just calculating these, I got 0.97 on the right side. So we know that we need to go a little bit larger. So next I tried 450 nanometers, which gave me a closer value, but still not there. So then we tried 500 and we got a really close number. So then I started decreasing the size that I was gaining. So then I chose 510 and we came out with the perfect value. So that is the answer. The maximum length is 510 nanometers. Guess and check is used for a couple of different heat transfer problems. It's just a type of solution when you have complex functions that require solutions of your variable, which are in deeper issues. So like the issues here where that L is embedded in the hyperbolic cosine and hyperbolic sine. Casual geometry or algebra would probably take a really long time to get the L out of that function in order to actually solve for it. So guess and check is the way to go on this one. Yeah, that's it. Thank you. Have a good day.